Off we go. So why impedance match? Why do we have to do this? Why is it so important? Why does it come up so much? So let's start with talking about what impedance is. It's just the ratio of voltage to current. That's it. That's the whole thing. Thank you. Good night. That's the definition of impedance. It's how hard you push to how much you get. And there are a lot of mechanical analogies to impedance that maybe we're more familiar with. It's one thing to talk about voltage and current. You can't really see these things. But mechanically, it's the ratio of torque, the twist, to the rate of rotation. So how hard you push to how much you get. And that's what mechanical impedance is. That's one of the definitions of mechanical impedance. And a vehicle transmission is an impedance converter. That's what it does. It's a gearbox. It transfers power from.
I think you just lost your audio.
Did I lose my audio?
No.
No, I didn't. Somebody lost my audio. Okay. I'll back up a minute. Vehicle transmission is an impedance converter. That's what it does. Mechanical impedance converter. It transfers power from the engines to the wheels. And what it does is it changes the combination of torque and rate of rotation so that the engine always runs close to where its optimum impedance is. Just like tuning up a transmitter, that's what your transmission does in a car, so that your engine runs at 2,000 or 2,500 RPM or 3,000, whatever it likes, wherever it's optimized. The transmission takes that combination of torque and rate of rotation and changes it to a different combination of torque and rate of rotation at the wheels. So when you're driving around and you hear that what's that is your transmission performing impedance conversion, and it's just matching the engine impedance to the wheels. The idea is to maximize power transfer so that whatever is generating the power, whether it's an engine or a transmitter or it's an amplifier or whatever, or an antenna working back into a feed line. So maximize the power transfer into whatever the load is. Now I have to digress for a second, and people say, you mean that the power generating grid has matched the impedance in the generator to the impedance out there in the grid? No, it doesn't work like that. If you did that, what they don't tell you in the maximum power transfer theorem is that both the load and the generator will then dissipate equal amounts of power. So you do not want to dissipate half of the nation's grid power in the generator. So this is a case where there is no impedance matching at the generator, just a side note. So you want to reduce feed line loss. That's an area where we impedance match a lot. You want all of your energy to start at the transmitter and go to the load and go out into the ether without any bouncing back and forth. You want 100% of that power to get through the cable and out the other end. So that's why we impedance match at the antenna. And it also makes transmitters and amplifiers happy. No doubt, if you've got a solid state transmitter or amplifier, and most of them are now, as SWR goes up and the impedance gets farther and farther away from 50 ohms, the transmitter will automatically throttle back its power. And that's not a power dissipation thing. It's generally to protect the amplifying devices from excessive voltage or current caused by the improper impedance. As the joke goes among RF designers, an RF power amplifier is always 1/2 cycle from total destruction. So you want to make sure you don't have too much voltage or current. But when SWR goes up, meaning impedance is not 50 ohms, that transmitter is going to throttle back just to make sure everything's safe. Okay, consequences of not matching. Well, we talked about this for a second. elevated SWR in a feed line increases loss. Why does it do that? Well, if you have a higher SWR, meaning that the load impedance out here is not 50 ohms or 75 ohms or whatever your transmission line impedance is, that means when you pump power in one end, it's going to travel through the transmission line, and then some of it's going to be reflected back. Well, then it gets back to the transmitter, it gets reflected again, and it goes back the other way. And basically, it's an infinite number of trips back and forth until it's finally radiated or burned up as heat. So elevated SWR means more trips through the line, and that's bad. Now, SWR also raises peak voltage in the line, and you can get some really high voltages as the transmitter keeps pumping power into this thing, and the waves start bouncing back and forth. So you're basically pumping power into this tank circuit caused by the feed line, and the voltage gets higher and higher and higher, and it can arc over. But it also causes loss through the dielectric. The voltage between the shield and the center conductor, it's like a capacitor there. So the loss in the dielectric goes up. It also causes the current, the peak current along the line, to go up, and that causes I squared R losses in the conductors, and skin effect does not help us out there. It's in that very thin layer along the surface of the conductor. So high current causes loss, and it also reduces your usable SWR bandwidth. The transmitter isn't going to be happy if you have an SWR above 2.5 or 3 to 1. And so the higher SWR is at the load, the narrower the range of that SWR curve in which your transmitter is happy gets narrower and narrower. And unhappy transmitters reduce power for the reasons that I just talked about. Mismatches can also reduce circuit performance. Maybe you don't get as good a filter performance, ultimate rejection, or a notch filter, or a peak, something like that. It just doesn't work as well because it's not working into the load that it expects. That can cause problems. And if we're talking about an antenna talking to a feed line that comes into a receiver, a mismatch there can reduce sensitivity because not all of the received power in the antenna gets transferred to the transmission line. So all kinds of things can happen from not matches, but it does not, by itself, a mismatch does not increase RFI, and it does not cause noise pickup by itself. Now, other things that cause SWR to go up can result in these things, but SWR by itself doesn't cause RFI or noise. It doesn't change your antenna pattern. The antenna is what it is. And if you have a high SWR because its feed point impedance is not what you expected or what the transmission line expected, that doesn't change the antenna pattern at all. There may be something wrong at the feed point that causes common mode current to flow on the cable or something else, and that might change the overall pattern of the antenna system, but it doesn't change the antenna pattern itself. And if you don't have a match, it doesn't cause bad breath. Nope. Or embarrass your mother. So don't worry about that. Okay. Now, if you want a really good video explaining SWR, go to YouTube and look up the AT&T archives. Search for similarities in wave behavior. And this is done in the early 60s. It's an old black and white film. It kind of reminds me of Mr. Wizard. And the guy teaching it is Dr. Shive, and he's got a black jacket and a little tie and everything. But he's got this wonderful presentation. It uses a thing called the Shive wave machine, and it shows waves moving along the structure. It's very visual, and he demonstrates the basics of waves moving along a transmission line. It's really easy to understand. The math is very, very simple. There's no hyperbolic trigonometry. There's no integrals. There's none of this. It's all just simple ratios. And he explains things like SWR and velocity of propagation and reflection. You can see them right there on the screen. It's about a 45-minute presentation. It makes a great club program. And everybody gets it, from rank beginners, I've shown it, to graduate level communications engineers. They're all totally fixated on this. It's really excellent, introducing these fundamental transmission line concepts. So check that out. And by the way, the slides of this presentation are on your website. You can download them, and you don't have to worry about writing all this down in notes. One question that comes up all the time is, why do we match to 50 or 75 ohms? Where did these numbers come from? Did they come from the sky? Did Hiram-Percy Maxim dictate them? What's the deal? So there are different optimum impedances in air-insulated coax, which was the first type of coaxial cable. It wasn't really a cable at all. What it was is plumbing with big tubes and little tubes, and the little tubes were supported by little ceramic insulators and stuff. But what they found was, in the math for this, there are different optimum impedances depending on what you're trying to optimize. There's an optimum impedance for loss, there's an optimum impedance for power handling, peak voltage, and other things. And if you do the math, then you come up with something around 30 ohms is the optimum for power handling. If you want to get the maximum amount of power through a transmission line like your shortwave broadcast station, 30 ohms, that's what you want. If you want to minimize loss, 70 ohms is the optimum for that. And that's why cable TV and other long lines use a 75 ohm system, because they have lower loss. But 50 ohms became common in the 1930s. Why? Well, it was a line that you could make easily from standard tubing sizes. And you didn't want to have special tubing. It was expensive. It was just as easy to use the standard copper pipe. And what came along was plastic, nylon, followed by polyethylene. And that invention, they made good insulators. It was easy to make a coaxial cable that would use plastic as its center insulator and its jacket. And if you ever get a chance to watch a machine that makes coaxial cable, I highly recommend that you look at it, because it's a really fascinating process. So anyway, I said, okay, well, we got 30 ohms for power handling and 70 ohms for loss. What do we do? Well, basically, you split the difference, okay? And 50 ohms, it was easy, it was convenient, it was right in the sweet spot between the two optimums. Problem solved. So good compromise performance. And then World War II happened, and we basically made an infinite amount of 50 ohm coax. RG8U was the standard, and there was so much of that, it basically became the de facto standard during and after the war, and we've never looked back. 50 ohms, polyethylene, foamed or solid. It has good power handling and loss, and that's where 50 ohms comes from. Okay, so how are we going to match? You've got this cable, for example, and you've got this circuit or this antenna. They don't have the same impedance. What are you going to do? Okay, well, you have to first decide whether you're going to do the match with resistive means, meaning you're going to use resistors, or are you going to do it with reactances? Now, you can use resistors to do an impedance match. Say your load is 25 ohms and your amplifier is 50 ohms. Well, you can make that amplifier happy by putting 25 ohms in series with the load, and you've got 50 ohms. That's great. But it's going to dissipate half your power. If you've got power to burn, so to speak, then resistive matching is pretty cheap and effective. That's why you use these attenuator pads and audio systems. And if you look at a lot of radios, you'll see a 3 dB pad or a 6 dB pad or something like that. They present the same impedance on each end, but they soak up some of the signal. That's what's in your receiver as an attenuator. But typically, we don't want to burn up RF power. RF power is expensive, whether you're trying to receive a really low signal or whether you're trying to put out a really big signal. You don't want to throw away your RF. So there are certain ways of doing resistant impedance matching. 50 ohm attenuators, T and pi network pads. These are described in the handbook. You can just put a parallel resistor in series, or a parallel resistor across a load, and you can lower a high impedance. You look at the TFTD folded dipoles that are so common at MCOM. They have this really nice SWR curve all across the HF spectrum. They're basically a folded dipole with resisted center loading that keeps the wild swings in impedance from causing big mismatches. It basically swamps out those impedance variations, so you wind up close to 50 ohms at the feed point. And another way to do it is just have a really long run of old coax, okay? If you look at your antenna, right at the antenna, you haul your SWR meter up the tower and you plug it right into the antenna and you get this nice SWR curve. The farther away you get from the antenna, down at the base of the tower, basically at your entry panel, back at the station, that SWR curve will get lower and flatter as you move away because of loss in the coax. Your SWR meter, whatever it is, measures how much you're sending out versus how much you get back. And if the coax is got some loss, and all does, that means less comes back. So it looks like your match is better and better and better. And old coax, or even new coax, if your frequency is high enough, makes a great dummy load. I've seen a number of labs that are operating at microwave frequencies. Where's your dummy load? Oh, it's just that big spool of cable over there in the corner. 1,000-foot spool of RG58 makes a really great dummy load at a couple or 3 gigahertz, for example. So be aware of that. You can also match with transformers. Here's your basic transformer schematic symbol. I'm going to grab my pointer here. Here are the windings, the primary and secondary windings. It might have a magnetic core, most do. And then you've got the voltage in and the current in, and the voltage out and the current out. And so the turns ratio is the secondary to the primary turns. And you can see that voltage changes. The voltage out is equal to the turns ratio times the voltage in, and the current out, whoops, sorry about that, the current out is equal to the current in divided by the turns ratio. So remember, impedance is the ratio of voltage to current. So if we change that ratio, we're also changing the impedance. You can get broadband transformers for RF and audio and modulation, and they often use ferrite and powdered iron cores to do their magic. And all they're doing is transforming the voltage to current ratio, and you can see this equation here. The impedance of the secondary divided by the impedance of the primary is equal to the turns ratio squared. So, for example, if the turns ratio is 2, I have 10 turns on the secondary and 5 turns on the primary, then my impedance ratio is going to be 4. And I can flip that around and I can have an impedance ratio of 1/4. It's 4 to 1 in one direction or another. All I have to do is turn that transformer around. N equals 3. My impedance ratio is 9, et cetera, et cetera, et cetera. And yes, you can have half turns and intermediate values of the impedance ratio. And in-fed half-wave antennas, they often use an N equals 7 to 1. That causes an N squared or 49 to 1 impedance ratio, and that's what does the magic, matching your 50 ohm line up to the 2,000 to 3,000 ohms of impedance at the end of a half-wave antenna. I wrote an onallbands.com column about this that explains how this transformer works. Steve K1RF did a really good job of explaining it. All you have to do is search for K1RF and InFed half-wave, and you'll find his excellent presentations. Basically, you can match coax to window line with n equals 3 to 1 for a Z ratio of 9 to 1. So 50 becomes 450. Now, I have to caution you, just because you have 450 ohm window line does not mean that the impedance presented at the output of that line is going to be 450. If it's matched, it will be, but window line can be mismatched just like coax. Here's some schematics. You can see you can have multiple windings. This is a picture of a switchable transformer. That's what the terminal strip is at the left, and the little relay. It can select between these different windings. So you have ratios of 1 to 1, 4 to 1, 9 to 1, and 16 to 1. That's a handy thing to have when you don't know exactly what your impedance is going to be at the antenna. And you can have balanced, unbalanced, and all kinds of other things. Let's take time out to talk about balance. Okay, this is a big topic for me. A balance is a function. It's not just a device, it's a function. And balance is an abbreviation of balance to unbalance. And that can apply to either the line or the load. The line can be balanced, the load can be unbalanced, or vice versa. When we talk about balance, that means both conductors are electrically symmetric with respect to ground or whatever the reference voltage is for the system. Open wire line is balanced because each one of the conductors has basically the same impedance to ground. A free space dipole has two legs that, if it's just in free space, they have the same electrical characteristic. You have a dipole that's above real ground and it's exactly symmetric, goes up in the air, and the legs are nice and straight and level. That can be pretty well balanced too. Unbalanced means the conductors are electrically asymmetric. Coaxial cable, typically the outside conductor, the shield, is connected to the system ground reference, either through enclosures or directly to a ground plane or a panel. Single wire lines, where you just have an output coming from a circuit that goes off to wherever, that is definitely unbalanced. Any system that has the enclosure return, meaning you screw the transmission line onto the enclosure, one of the conductors is connected to the enclosure, that's an unbalanced system. Ground plane verticals, where you have one radiating element, or the rest of it is some kind of ground screen, that's also an unbalanced system. So the function here is to isolate the balanced and unbalanced systems while transferring power between them. Anything that you do that performs that function is a balance. It doesn't have to be a coil, a transformer, whatever. There's a zillion different ways to do this. There are a lot of different types of balance. But that's a function. It's not necessarily a device. It can be a device that performs the balance function, but that's as far as you can go. And un, which you will also see, is something that operates between two unbalanced systems. And you can buy little impedance transformers with a PL259 on each end, and you screw on your cables. That's an un, because both terminals on each side are asymmetrical electrically. Okay, there are current balance, and basically the idea is a current balance. What it does is it forces current. Think of that dipole up there with its two terminals, its two legs. A current balance will force equal current in each one of the terminals of that dipole. And when you force equal current into each leg radiates equally, and that gives you the nice donut pattern that you want. A voltage balance forces equal voltages in load terminals. And that it sounds like it's totally equivalent, but if each one of the load terminals does not have the same impedance, you won't get the same current. For example, if you have your dipole, and like most dipoles I know, they're not completely symmetric with respect to ground. One end is higher than the other, or something like that. Okay, the different legs have different impedances at the feed point. If I drive them with equal voltages, I'm not going to get the same current in each leg. So the voltage balance isn't typically as effective for antennas. There are Guanella and Ruthoff transmission line balance, and those are made out of parallel wire, and they are wrapped around some kind of magnetic core, and the way that the windings are connected together creates a current or a voltage balance. And a full discussion of this topic is well beyond the scope of this presentation. Where I can send you for a complete discussion is chapter 5 of the handbook, and the very first chapter is RF techniques, and it has all sorts of stuff from this talk in it. So if you have the multi-volume handbook set, it's in volume 2, and this is also discussed quite a bit in the antenna book chapters on transmission lines and transmission line systems. There are also interesting ways of using transmission lines to create this balun effect, sleeve balance. Anybody out there might have a VHF dipole, a vertical dipole, or remember the old isopoles that had the conical hats that came down. Those are effectively transmission line sleeve balance, and they create a high impedance on the outside of the feed line so that the current radiates only from the antenna element and not from the feed line. A choke balun does it basically the same thing. You can do it simply by winding the coax into a single layer or scramble wound coil, and that creates an inductance in the outer surface of the feed line, and that acts to reduce or block the common mode current path. So an impedance transformer, which may change the ratio of voltage current inside the feed line, is not necessarily a balun, and vice versa. You can make a 4-to-1 current balun, for example. Sometimes you can make both functions happen at the same time, but not always. So be cautious about what's referred to as a balun versus impedance transformer. Thank you. I feel much better now. Okay, so let's jump over to reactive matching. That is by far the most common way of impedance matching. All that means is I'm using inductors and capacitors that present reactances and very little in the way of resistance. And then when I talk about networks, that's a fancy name engineers use for circuits. So when I talk about a L network, for example, what I'm talking about is a circuit whose schematic looks like an L. It doesn't sound nearly as impressive when I use the second definition. So the most common reactive matching circuit is in fact an L network. We'll get into that and these others in a minute. And then you can have pi and pi L networks and T networks. The schematics look like the letter pi or the letter T. The T is by far the most common used in antenna matching circuits. If you buy a standalone tuner, it's probably a T. If you're using a automatic tuner, it's probably an L. You can also use a tap coil LC tank circuit or just a shunt inductor. The old parallel LC circuit was used for voltage feed on wire antennas, very popular for many years. You basically just move the tap around. You adjusted the circuit to resonance when it was connected to the antenna, and then move the tap around until you got the most current in the antenna, or the most fire came off the feed point. Both were fun. And then the shunt inductor, that's what a hairpin match is. You're just putting a coil across the feed point, and that alters the impedance of the load. The networks can be a high pass. If they have a series capacitor, then they have a frequency response that means higher frequency signals will get through better than low frequency signals. T networks are high pass, or they can be low pass if they have a series inductance, which its reactance gets higher with frequency, so the frequency response drops off at higher frequencies. Reactive matching is usually designed or adjusted to work at just one frequency. You basically, you turn on your transmitter, you fiddle with the controls until SWR comes down to 1, and then you stop. And if you change frequency a lot in your transmitter, SWR will go up, so you twiddle the knobs again, and SWR comes down again. So these are sometimes referred to as resonant matching, but reactive matching usually works at just one frequency. Let's talk about the L network. It has two components. Usually it's one L and one C, but there are also L networks with two inductors or two capacitors, and those are used in special circumstances. The L network transforms impedance from high to low or from low to high, depending on the orientation of the components. So if you have an L network and it is not, you're not able to achieve a match, no matter how you twiddle the knobs, just turn it around, swap the input and the output. It's probably trying to match something that it can't, but if you turn it around, you might be able to affect that match, and we'll see why in a minute. If you have an L network with a series capacitor between the load and the transmitter, it's a high pass L network. And if you have a series L, it's a low pass network. Oh, here's the Smith chart. And you knew I was going to work in a Smith chart, didn't you? I left out the really complicated parts of the Smith chart. Up at the top, you can see 4 different variations of the L network. Here's one, Z of the device and the Z of the line. Device and the line, device and the line. Think of the device as a transmitter. This one has a shunt C and a series L. This one swaps the L and the C. This one moves the capacitor to the output, and this one moves the inductor to the output. And if you look at the Smith chart, you will see that if you color in half of it so that it looks like a yin-yang, this circuit can take any of the reactances, the impedances in this part of the Smith chart and transform them to the impedance of the line. So you get, this is a 1-to-1 match right here. So you want to get this impedance matched to this impedance. That's what this circuit can do. And all 4 of them, you can see, match different areas of the line. And for example, like I was telling you before, if you switch input and output from this one to this one, you can see that this one over here can match this side of the Smith chart down here, whereas this one can match this one. And since all impedances are somewhere in this circle, okay, and if you split it into these 2 circuits, these 2 types of circuit can match any kind of impedance that you've got. It's just a matter of convenience and what's expensive. Are the components reasonable? Have you got any? That kind of stuff. So you have 4 options. These are the 2 capacitors down here with the capacitor on the input, the output. This is sometimes referred to as an omega match. And this is also a similar thing. Yes, it looks like a butt. So anyway, these are all things that you can see on the Smith chart. Here's the pi network, which is 2 L networks back to back. If you take this red line right in the middle and you cut half of the network away, the other half that's left looks like an L network. So it's 2 L networks back to back. Why do you do that? Okay, back to our transmission analogy. If you've got a 2-gear gearbox, okay, a big one and a little one, at some point you get to the point where one gear is so big and the other one is so small that it's not very effective, and it's lossy and it heats up and all this kind of stuff. The same thing can happen with an L network. Also, it's got and the wider the apart the two impedances are, the narrower the match is. So to improve the range and what's called the Q, meaning the breadth of that matching network, they invented the L network. So it's like having invented the pi network. It's like having a little idler gear in between two other gears. It may not, it costs another gear, but it allows you to match more impedances over a wider range. This is common in tube amplifiers, lots of pi networks there. And sometimes you use one additional L in series with the output. So there'd be another inductor right here. And they do that so that you get better harmonic suppression. Remember, if the L network, if the inductor is in series, then it's a low pass network. So by putting one more inductor in series, then you can suppress the harmonics at higher frequencies. Here's a T network. This is typical of most antenna tuners sold today. It can also be thought of as a pair of L networks. You can split this inductor. If you have two identical inductors that are in parallel, they combine to make this one inductor of half that value. So you can think of this again as a pair of L networks back to back in the shape of a T. And it's usually in a high pass configuration with an input and an output capacitor. And it's done because variable capacitors are a lot cheaper than variable inductors. You could make a T network out of two inductors and a capacitor just as easily, but it's cheaper and so less expensive to you, the consumer, to use input and output variable capacitors. Transmission line transformers. This is another interesting way of matching impedances. These are called synchronous transformers. And the reason they're called synchronous transformers is they set up a set of reflections. If you look at this drawing here, I have different impedances of transmission line. This impedance here and here are different. And this one is yet another impedance. And at each interface here, I set up a series of reflections. It's just like I connected the transmission line to a load. And so what I wind up with is a whole bunch of reflections going back and forth in these transmission lines. And when you add them all up, they partially cancel. And the result is the impedance, which is just the ratio of voltage and current. The impedance is the design impedance that you want. The most common one in ham radio is called a quarter wave or Q section. If you've got an impedance Z2 and you want to match it to a different impedance Z1, and this can be an antenna or a transmission line, then if you can get a quarter wave length of coax with an impedance of the square root of Z1 times Z2, called the geometric mean, then the series of reflections that are set up will match Z2 to Z1. For example, if you have a full wave loop, it might give you an impedance of somewhere around 100 ohms. Okay, that's what we've got over here. And we want to match it to 50 ohms over here. So what do? Well, we multiply the two together. That's about 5,000. We take the square root, and that's about 70.7 ohms. Don't ask me how I know that. So have we got any cable that's around 70.7 ohms? Well, of course we do. We've got a 75 ohm RG9 or RG11. Those are very common. And so if this is on 40 meters, for example, I might cut a 23-foot something piece of RG11 and put connectors on it and connect it in between my antenna, which is out here at 100 ohms, and I'll get a pretty good match at 50 ohms back here for my regular feed line. So that's called a quarter wave or a Q section. This is all discussed in considerable detail in the antenna book section on transmission line systems. You can also use 1/12 wave sections, and these are useful for when you're trying to match 50 ohms to 75 ohms. For example, you've got a 50 ohm antenna out there on 2 meters, and somebody gave you a whole big bunch of 75 ohm hardline. Well, if I just hook it up, I'm going to have an SWR of about 1.5 to 1. And I don't really want that because I don't want to lose transmitter power. I want the maximum sensitivity. So as it turns out, you can cut 2 short pieces, 1/12 of a wavelength long, and hook them in series. That's what's described down here. And voila, you've got a match. Now, these are single frequency matches, so they only work perfectly at the frequency at which the matching sections are exactly the electrical wavelength specified. And as you get away from that frequency, the match is not as good, but it's generally broadband enough that makes a pretty good match. These are called synchronous transformers. There's a whole lot more than 1/4 and 1/12 wave, and there's a lot of tricks that the RF engineers have come up with. Okay, now let's talk about feed point matching right at the antenna. There's all kinds of structures that you have seen, gamma matches and hairpins and all sorts of stuff. There's also transmission line techniques where you can use these synchronous transformers and other stuff right at the antenna. These mount right at the antenna, or maybe they're part of antenna feed point assembly. And you got to get up there and adjust them right at the antenna. So you're up there hanging on for dear life with one hand, fooling around, adjusting the gamma match with the other one, and yelling down to your assistant, "How's it look now?" So that's one of the nice things about all these new antenna measuring things that you can put in your pocket and take right up the tower with you. But you still have to adjust them right at the antenna. They are single band matches. They're not wide band matches. Here's the first one. This is the oldest one, called a delta match. And you can see the transmission line, 600 ohm transmission line came up. Well, where are you going to connect it to the antenna? Well, right in the middle, if you connect it right together, you'd have a really low impedance. And that wouldn't do because you'd have a high SWR to 600 ohms. Well, way out at the end, you have a really high impedance. Maybe it's 2,000, 3,000, 4,000 ohms. Well, that also creates a high impedance with 600 ohm line. So somebody got the bright idea that says, well, in between really low and really high, there must be some spots on there that present a 600 ohm load. So basically, that's the idea. You just move the wires apart until you get the 600 ohm point. And typically, for these half wave antennas, A is 0.12 wavelength and B is 0.15 wavelength. That will get you in the ballpark. And so basically, you're just trying to find the right point on the antenna that gives you 600 ohms. Some of you will have seen slant wire feed for verticals. This is common for broadcast antennas, where the transmission line comes in from the side and it stops, and then a wire kind of slants up to the antenna and hooks onto that tower someplace. That is a delta match, but only half of it is used because this part is the antenna and this part is in the ground plane. Here's a T match. It's like the delta match, but it's a little easier to deal with and you don't have to move the feed points around. So basically it started out looking like this. Why do we have to have a triangle? Well, we don't. We can run it up, we can run the wire along the antenna and then connect it to the antenna. This is the way it's usually done today with 2 series capacitors, and you get up there and you tweak them until you have the right match. It constructs a short piece of transmission line on each side of the feed point, which is down here. And it also modeled as just a folded dipole. It kind of looks like folded dipole here with some extra wire attached on each end. So you can model it that way. The T-match isn't as popular as it once was. The gamma match is still very, very popular. It's 1/2 of a T-match. If you flip that gamma match around on the other side, you'd have basically a balanced match, a T-match. And what this gamma match allows you to do is, this was a big deal back in the 50s and 60s. It was called plumber's delight construction, meaning all the metal was simply bolted or soldered together. And so this allowed your coax to come up from the station, and then right at the middle of the element, where you have a very low impedance, you could connect the coax shield right there, and it would not upset the operation of the antenna. So basically, it's one capacitor in series with the feed point, and you've got this little piece of transmission line here, and you adjust it until you get the right match. And you have two things that you can adjust. You can adjust the length of the tube. Typically, this is a concentric tube with a piece of wire inside of it, and you can also adjust the distance back and forth. And those two things allow you to find the right impedance and the right bandwidth. So there's a big section on this in the antenna book about how to do this. Gamma match and shunt feed towers are exactly the same thing. Just like the delta match, you can take all this and set it on its side, and that's what a shunt fed tower is. It's a gamma match. Beta match is also called a hairpin match because a lot of the beams, the inductor here in the middle was just a piece of heavy wire that went up and made a little loop and kind of looked like a hairpin. But the insulated, the driven element has to be insulated. This is no longer something that you can connect to the metal boom. But the center of the symmetrical hairpin can be grounded because that's an electrically neutral point, and a lot of antennas do that. They have a terminal or a hole right at the end of the hairpin, and then you can attach it to the beam without upsetting things electrically. And that keeps the hairpin from flapping around in the wind and eventually breaking. Basically, what you start with is a driven element that's slightly capacitive, and so that looks like the capacitor for the L network, and then the inductor, which is this part, the hairpin, that makes the rest of the L network. So this is really an L network in a funny looking form. And then you put a 1-to-1 choke balun here to isolate the coax from the antenna and keeps the outside surface of the coax from affecting your match. And so that's what a beta match is. Now we have a lot of references and tools to work with out there. You've got the ARL handbook and the ARL antenna book. The antenna book software includes a program called TLW, which is Transmission Lines for Windows. And I believe it will run in a command line interface or as a standalone .exe file, even for Windows 10 and 11. There's also some software called Match and a variety of other useful little gadgets out there. There's a lot of stuff online too, but the TLW is really the star of the show. It's written by Dean Straw, N6BV, my predecessor as editor of the antenna book. And Dean has done a tremendous amount of excellent work. We awarded, we meaning YASME, gave Dean an excellence award for all his contributions to the antenna book, and there's still a lot of his material in there. If you've got an antenna book, look up TLW. It's part of your download package, and it's really worth running. The book ARL Guide to Antenna Tuners by Silent Key W1ZR gets into a big discussion of the different kinds of tuners, how to attach them, how to adjust them, and gets into discussion of loss and all this kind of stuff. It's a really good book if you want to learn about antenna tuners. The ARL online archives of QST, QEX, and NCJ are also available, and they are really good. Once you start finding references to these articles, go back, find the original article, look for those authors and search for them. There's probably more material out there. It's one of the best kept secrets in ham radio is ARRL members have full access to over 100 years of this stuff. And NCJ in particular has some really good practical antenna articles. We're printing some more by Al Chrisman, K3LC, for example, in the edition that, or the issue that's just come out, and follow up in the next edition. Ham Radio, the old magazine Ham Radio, it's also searchable, but it's not archived. You'll have to look in the Internet Archive in what's called the Wayback Machine, and you can find those issues online. There's 8 volumes of the ARRL Antenna Compendium, and there's a lot of really cool papers in there. One of the things that is in the antenna book that nobody seems to know about, I went through all of that stuff, assisted by my son Webster, KD7DQO, and we went through all of the antenna compendiums and all of the other antenna books for the ARRL and listed all of the antenna projects in a spreadsheet. So you can go in there and search them by topic. They're grouped by, are they HF, are they VHF, are they wire antennas, are they beams, or are we talking about transmission lines? All that kind of stuff, you can find them, and then you can go get the article. And then there was this hands-on radio column by this N0AX guy and QST between, I think it was 2005 and 2018. And so there's 180 columns, a lot of which are about antennas and transmission lines in there. That is one of the things I often go to my local club meeting, and I'm there for the hour before the meeting just to stump the Elmer, just to mentor people. And the questions that come up over and over again by far are antennas and transmission lines, things like that. So more references and tools. Here's a great book, Transmission Line Transformers by Jerry Sevick. He's the guy that really brought this kind of transmission line transformer to amateur radio back in the 70s and 80s. He was a senior engineer for, I believe, RCA, and it's an excellent book, really explains how they work. The series by Walter Maxwell, W2DU, Reflections 1, 2, or 3, any of the editions is worth reading. The first series was based on QST articles that came out in the 1970s, and then he just kept adding on to that. So any of those are really good. LB Sevick, W4RNL, another silent key. I think it's bad luck to write about antennas. That's what I think. www.sevick.com, his comprehensive website, is now available. I think antennax.com online is also possibly out of business now. I should have checked that today. But if you search for LB Sevick's articles, you'll find literally hundreds of them. A lot of antenna designs and explanations. There's also online calculators at RF Cafe and Microwaves 101. Those are very good, help you design your antenna. And there's some free classic textbooks that are available online. Wherever you go in amateur radio, you will find Radio Engineering by Terman to be cited as a primary reference. Fred Terman was a professor at Stanford during the late 30s and throughout the 40s and even beyond. And his books were the Bible for radio engineering in many fields. Radio Antenna Engineering by Laporte is another one and covers all kinds of things. And you can also see the Antenna Fundamentals section, the first volume of the antenna book. Then you can get into, never far away here, you can get into Antennas by John Krause, W8JK. He's the guy that invented the 8JK antenna. And the Antenna Engineering Handbook, there you go, by Johnson and Jasek. Those are also out there. Go to your library book sale, look through the reference books, online, eBay, all this kind of stuff. these things are good to have around for the interested reader. So thanks. I have given you kind of an overview here of impedance matching, what it is, why we do it, the different techniques that are out there that are common. And I guess I can take some questions. I think Marty was first in the pileup. Go for it, Marty.
Oh, only online.
There you go.
Okay, thanks, Ward. Great talk, and a good reminder on all those resources that are available. You mentioned you were talking about making a choke just to keep the RF from coming down the coax, and you said, you know, wound or scramble wound. My recollection is that scramble wound will result in lower performance because you end up getting too much capacitance between the windings. One of the references that you know that may be also applicable is the series of articles by W9YC
K9
Jim
YC.
Brown.
Yep.
Sorry, K9YC Jim Brown, and he definitely says these turns need to be in order, even if you have to overlap at the end, but not scramble wound.
Yeah, scramble wound is convenient, but not particularly repeatable. And it doesn't always work on the bands where you think it's going to work. It's like a little tuned circuit because of the distributed capacitance that you mentioned. And so it's only going to work on some of the bands. If you look in the antenna book, there's a table. Let's see, where is that table? I think, is it in this volume? Yes, transmission line systems techniques. And so there's a series of tables and stuff. Coiled coax choke balance, it's table 24.13. Now, scramble wound is when you just grab the cable and you wind it up like an extension cord. Over, under, over, you know, you just wind it up the coil and you tape it up, and there you got a coil. Okay, but it's going to be highly variable. It depends on the diameter, the number of turns, how the turns are arranged, what type of cable. So this table here has some optimized values of length of cable and diameter for scramble wound coils. A better way of doing it is a single layer solenoid, meaning you have a coil form like a piece of PVC pipe or a Coke bottle, and you just wind the coil around it and then put tape on it, fold it up. It's much more repeatable. It'll give you much better performance. But the best of all is to use a wind the coil on a ferrite core. If you want to hear more about this, Jim Brown wrote a lot of the antenna book material on these choke balance, and they're just RF chokes, and we use them as balance. And if you go to his website, k9yc.com, and you look for his tutorial on ferrites, you will get a lot of balun information. Plus, he's got several presentations and papers on the subject, a wealth of information. Thank you for bringing him up, Marty. Really good stuff.
Yeah, thank you, Marty. Anybody else got any questions out there? You want to raise your hand?
I think Dan does.
I put the link to the video on YouTube in the chat.
Okay. Thank you. Dan, did you have a question? All right, not all at once now. Okay. Any other questions out there?
Dave New made a comment about a quarter section of 75 ohm works to match a 50 ohm coax to 150 ohm full wave quad driven loops.
Yeah, it'll match anything between 90 and 150 ohms. You would think, oh my gosh, that's such a wide range. The SWR must go really nuts, but it really doesn't. Your SWR will be less than 2 across that range. So it's a very handy thing. If you've got a rainy day and some spare coax, cutting a few quarter wave sections and tuning them up with your antenna analyzer is a great way to go. Then you have them all ready to go in your toolbox.
He also said the CBIC archives are online. He posted the link.
I'm sorry, what was that, Barry? You're a little garbled.
The CBIC archives are now online, and he posted the link.
Okay. Oh, good. On the RATPAC website. Excellent. Thank you.
That's
Anybody
everything
else?
in chat.
Anybody else got any questions? Want to raise your hands, you know?
I think
Was
I
it the chat?
showed everybody good.
Okay, it's like Dennis has got his hand up.
Well, not a question, but just I want to thank Ward for joining us tonight, and really appreciate. This was a great presentation. Well done, well done, and I hope folks got a lot out of it. There's a lot of great information, and really appreciate you being here this evening for that. So,
Glad you enjoyed it.
oh yeah, and we'll definitely. I think we'll get you back again. I'll work on you.
Okay.
We'll get you back for a third time.
Hey, we'll double team him.
There you go.
There you go. Yeah, you know where I live, right? Okay.
Might as well just say yes now.
Okay. Yeah, that's right. Sure.
Oh yeah,
Don't
that's wonderful.
won't wear out my welcome.
Oh, never.
Not going to happen.
Not
Okay, else got any questions out there? It was a great presentation.
Okay.
Thanks, Ward.
Thanks.
Thank you so much.
Ward.
See you on the bands.
All
Yeah.
right.
All
We'll be
right,
in touch.
with this, I'm going to say 73s and wish everybody a good weekend coming up.
Yeah, we're gonna be going on vacation for a month or so.
Yes, we will
So
not
enjoy
be
it, everybody.
any Rat Pack for a few weeks out now.
Yep.
Finally, all the ones that we had committed, we've gone through, and now we're going to take some time off and do some summer type stuff. So with that in mind, 73s everyone, and see you down the coax.